Hello students, welcome to the lecture series of rotational dynamics. The topic that we are going to see today is rolling motion. So let's start with the topic. Actually, this rolling motion is defined as a combination of translational motion of the body and rotational motion of the body. Where in translation motion, the center of mass of the body is shown to have velocity v, because of which all the points on the body gain the same velocity as that of center of mass. V, 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 and V. Now, let's move towards the rotational motion. The body in this rotational motion is shown to rotate about an axis passing through center of mass of the body. The angular velocity of rotation for the body is shown as omega. Because of this rotation, every point on the body also gains a linear velocity, which is r omega, whose direction is as shown in the figure. So, every point on the body which is performing rolling motion gets two velocities, one due to translation and another due to rotation. Okay. Now, there are different types of rolling motion, which is nothing but pure rolling and rolling with sliding. The rolling motion that we are going to study and concentrate on is pure rolling motion. Now, I have written the definition of pure rolling motion. Let's see what it is. So for pure rolling, the required condition is as follows. The point of rolling body which comes in contact with the surface, it must be at rest, which means that there should be no relative motion between the point which is making the contact with the surface and the surface itself. Now, this gives rise to a condition which is called as condition of pure rolling. Now, to derive that condition, we have to look at a diagram. So, the diagram has appeared on the screen, and we can see that the diagram consists of a body which is rolling on the surface. This is the center of the body. The body's center of mass has velocity v, and the body is rotating about the center of mass with an angular velocity omega. The point at the bottom, which we name A, is nothing but the point which is making contact with the surface. Now, this point A has two velocities, one due to translation motion and another due to rotational motion. So the one velocity that we have due to translation motion is v towards right, and the velocity that we have because of the rotational motion is r omega towards left. We have defined r as the radius of the body. Now, we said that for pure rolling, there should be no relative motion between the point A and the surface. The velocity of the surface is 0. Therefore, for no relative motion condition, the velocity of point A should also be 0. And when we say that the velocity of point A should be 0, it gives rise to a condition V must be equal to r omega. V must be equal to r omega. Now, this is not the only condition that is satisfied for pure rolling. There is another condition which relates acceleration also. So let's say the body has an angular acceleration alpha about the center of mass, and the center of mass is moving ahead with an acceleration a. So the another condition that must be satisfied for pure rolling is a must be equal to r alpha. So these are the two conditions, v is equal to r omega and a is equal to r alpha, that must be satisfied for pure rolling of the body. So I'll just box up the two relations. Now, an important point to note about rolling motion is that I'll write down the note over here. There is no relative motion along the surface, but but there can be relative motion. There can be relative motion perpendicular to surface. Perpendicular to surface. And this condition is required because we have to lift this point O upwards. We have to lift this point A upwards again for the body to roll. So there should be no relative motion along the surface, but a relative motion perpendicular to the surface is necessary. Okay. Now, an important point in rolling motion is nothing but the total kinetic energy of rolling motion. And as we have defined rolling motion as a combination of translational motion and rotational motion, the total kinetic energy of rolling motion is nothing but the kinetic energy translation plus kinetic energy rotation. Now, we know that kinetic energy translation is nothing but half m v square, and kinetic energy rotational is half I omega square. But the case is of pure rolling. So in the place of omega, we can write V by R. So the total kinetic energy for the rolling motion becomes half mv square plus half, in place of moment of inertia, we can write mk square, where I should be writing a small mk square, where k is nothing but the radius of gyration. K is nothing but radius of gyration. And in place of omega square, we can write v square by r square, because the case is of pure rolling. Now we can common out half mv square, and what remains inside the bracket is 1 plus k square by r square. So this is the formula for total kinetic energy in rolling motion, which is half mv square bracket 1 plus k square by r square, where k is nothing but radius of gyration. And this rolling condition is pure rolling, because if it was not pure rolling, we couldn't have used omega is equal to v by r. Okay, so now only a last topic remains in the series of rotational dynamics, which is nothing but rolling of a rigid body on an inclined plane. So let's quickly finish that topic and put an end to this lecture series. Okay, so let's start with the last topic of the series of rotational dynamics, which is rigid object rolling down an inclined plane. So I've shown on the left hand side of the screen a diagram where a rigid body is rolling down an inclined plane. I've specifically shown the force of static friction acting on the body. Now we all know that friction is a dissipative force, and therefore we cannot use energy conservation. But there is a loophole, because in this case of rolling down an inclined plane, the work done by the friction is zero. And why do I say that the work done by friction is zero? Because the point of contact, the point which is making contact with the surface, it is having relative velocity perpendicular to the surface. Therefore, the displacement of this point of contact is perpendicular to the surface, and therefore the angle between static friction and displacement is 90 degree. Therefore, Fs bar dot S bar is equal to 0, and we can say that the work done by friction is 0. Now, the work done by friction is 0. Therefore, we can easily use energy conservation principle, which is nothing but the initial total mechanical energy is equal to final total mechanical energy. The initial point over here is the point at the top, and the final point is at the bottom. So I can write down by total mechanical energy conservation. I can write down kinetic energy at point 1 plus potential energy at point 1 is equal to kinetic energy at point 2 plus potential energy at point 2. Now, initially at point 1 the object is at rest, therefore the kinetic energy is 0. The body at point 1 is neither having rotational kinetic energy nor it is having translational kinetic energy. At the bottom, the object does not have any potential energy because we define the base at the bottom. Therefore, the potential energy at point 1 becomes equal to kinetic energy at point 2. The potential energy at point 1 can be written as mgh. mgh. And the kinetic energy at point 2 can be written as the translational kinetic energy of the body plus the rotational kinetic energy of the body. Now, since it is the case of pure rolling, we can write down omega is equal to V by R. Omega is equal to V by R. So, mgh is equal to half m v square plus half. In the place of moment of inertia, I am writing mk square, where k is nothing but radius of gyration. And in place of omega square, we can write down v square by r square. So from all the places I can cancel out m. Transfer the 2's on the other side and I'll have 2gh is equal to v square. I'll common out v square, and inside the bracket now I only have 1 plus k square by r square. So the velocity finally, when the body rolls down to the bottom, can be written as under root 2gh upon 1 plus k square by r square. So this is the formula for velocity of the body when it rolls purely down an inclined plane. Okay. Now, the last formula that we have to derive is of the acceleration of body rolling down an inclined plane. Now for that, we use the third kinematical equation, which is nothing but v square is equal to u square plus 2as. Now initially the object is at rest, therefore u is equal to 0, and we have v square is equal to 2as. Now we just derived the formula for velocity at the bottom, which was nothing but under root 2gh upon 1 plus k square by r square. When we substitute this velocity in the equation, we get 2gh upon 1 plus k square by r square is equal to 2as. Now in place of s, we can write down h upon sine theta. So 2 and 2 gets cancelled, h and h gets cancelled, and finally we have the formula for acceleration, which is nothing but g sine theta upon 1 plus k square by r square. So thus we have derived the formula for both velocity of the body when it rolls down an inclined plane at the bottom, and we have also derived the formula for the acceleration of the body rolling down an inclined plane. So these are the two formulas. V is equal to under root 2gh upon 1 plus k square by r square, and A is equal to g sine theta upon 1 plus k square by r square. So thus we have finished all the important derivations and the proof of certain formulae in this series of rotational dynamics. The next series that we are going to start is nothing but the series of important derivations from board's point of view, 12th standard board's point of view, for the chapter of mechanical properties of fluids. Till then, thank you very much.